Good morning and welcome to the lecture number 15 of the course Water Resource Systems, Modeling Techniques and Analysis. In the previous lecture, we have introduced dynamic programming. Essentially, we started with a representation of a multi-stage decision problem and introduced the Bellman's principle of optimality. If you recall, a multi-stage decision problem is represented as shown here. The input state at a particular stage n gets transformed to an output state S n minus 1, in this case starting with S n, because of the decision we make x n, and this output state forms an input to the next stage n minus 1, and that gets transformed because of the decision x n minus 1 we make on the state S n minus 1 into S n minus 2, which becomes an input to the next stage, and so on. Because of the decisions we make here x n at stage n, you get a return of R n. Now, these returns in water resources problems can be either economic returns or physical returns in terms of the amount of hydropower produced, in terms of the crop yield that you accrue, in terms of the flood control benefit that you get, intangible benefits perhaps, and so on. So, the returns are a function of the decisions that you make x n at stage n, starting with the state S n at stage n. This is how we represent a multi-stage decision problem, and the optimization we do in dynamic programming for such a multi-stage decision problem is based on the Bellman's principle of optimality. Essentially, recall that it states, starting with a particular state at a given stage, you must proceed in an optimal manner until all the stages are completed, irrespective of how you arrived at that particular state. That means, as long as you know the state in a particular stage, you proceed in an optimal manner starting with that state. Do not worry about how you arrived at that particular state in that stage. So, given the state at a particular stage, you must proceed in an optimal manner until the end of the horizon. This horizon can be space, it can be time, and so on. And we started discussing the water allocation problem. For completeness sake, I will restate the problem, and then the stage 1 computations that we did in the previous lecture. We will just go through it again quickly. There are 3 users, an amount of water available of 6 units needs to be allocated optimally among the 3 users. The return that you get from a particular user for a given allocation is given in this table. For example, if you allocate 2 units of water to user number 3, you get a return of 8 units. If you allocate a amount of 2 units to user 2, you get a return of 6 units. Allocate an amount of 2 units to user 1, you get a return of 12 units, and so on. So, this table gives the returns that you get for a particular allocation. Look at this. If you allocate 4 units of water to user number 2, you get a negative benefit. Typically, this can be a irrigation user, which means up to certain point you keep on increasing the benefits, then beyond that it starts decreasing, and in fact, it may become negative in the sense that if you allocate more water than actually needed, you may suffer losses in fact. So, this is a type of benefit function that you may get. Now, these need not be always economic returns, they can be intangible benefits, they can be benefits in terms of the physical quantities, and so on. So, we started this example from stage number 1, where we include only one user number 1. We say that S 1, which is the state at stage number 1, is the amount of water available to be allocated to user number 1. And S 1 can vary from 0 to q, where q is the total amount of water available. In this case, it is 6 units. So, we solve this problem for all possible values of S1 because we do not know exactly what S1 will be. We are moving in the backward direction. So, we are asking the question, if S1 is equal to 0, how much should I allocate? If S1 is equal to 1, how much should I allocate? If S1 is equal to 2, how much should I allocate, and so on. So, we are solving the problem for a given value of S1 which is not known. We will know the actual value of S1 only when we solve the complete problem. And F1 star S1 is the optimized objective function value for a given S1 at that stage 1, where only one user is included. So, this is how we solve. We say S1 is equal to 0, x1 can be only 0. Recall here that x1 can take on values up to S1. What we mean by that is that if 3 units of water are available, you cannot allocate anything more than 3, and therefore, x1 can take on values between 0 and S1. So, we ask the question, if S1 is 1, whether we should allocate 0 or we should allocate 1, and the maximum benefits are 7 corresponding to an allocation of 1. Similarly, if S1 is equal to 2, you can either allocate 0 or 1 or 2. If you allocate 0, you get a return of 0. If you allocate 1, you get a return of 7. If you allocate 2, you get a return of 12, and therefore, the maximum benefit is maximum return is 12. Therefore, the corresponding allocation is 2. So, what it states is that if 2 is available, allocate 2, you get a return of 12. If 3 is available, allocate 3, you get a return of 15. If 4 is available, allocate 4, you get a return of 16. 5 is available, allocate 4, get a return of 16. Remember, if 5 is available, if you allocate all the 5, then you get a return of 15, whereas if you allocate only 4, you get a return of 16. Therefore, it says if 5 is available, allocate only 4. Similarly, if 6 is available, allocate only 4. I encourage you to look at the previous lecture, that is lecture number 14, for a detailed discussion on this. We will now proceed to stage number 2. In stage number 2, we are including 2 users now, user number 1 and user number 2 together. So, S2, which is the state at stage number 2, is the amount of water available to be allocated to user number 1 and user number 2 together. And X2 is the decision that we are making at stage 2. This is the amount of water allocated to user number 2. Because you make an allocation of X2 from the available S2, the amount of water available for allocation at the next stage, which is S1 in this case, as we are proceeding the backward direction, will be S2 minus X2. But we have solved this problem already. For all amounts of water available here, we have solved the problem in the stage number 1, and therefore, we know what is the optimal benefit that you get out of an allocation of S2 minus X2, and that is what we pick up. So, we write at stage 2 this recursive relationship, you understand correctly. At stage 2, the optimal benefit associated with the state S2 is given by maximum value of the returns that you get from user 2 for an allocation of X2, which is R2 of X2, plus the optimized return that you get for an allocation of the remaining amount of water, which is S2 minus X2 in the previous stage or the next stage in this particular case to user number 1. So, what does this indicate? This term indicates here the optimized value from previous stage. Remember, this is what we have solved already from the previous stage computations. This is what we have solved f1 star s1, which means given this argument s1 here, we know what is the x1 star and what is the maximum allocation here, maximum objective function value, and that is what we use here. I repeat again, given the state which is the amount of water available at stage 2 to be allocated to both user number 1 and user number 2 together, we make a decision on x2, which is the amount of water allocated to user number 2. We get a return of R2 x2, and because of this decision, we are left with S2 minus x2 for the next user, and we have already solved in the previous stage what should be the optimal value corresponding to S2 minus x2, and that is what we add here. So, this recursive relationship is in fact a statement of the Bellman's principle of optimality. Given the state S2 at this particular stage, we are proceeding in an optimal manner until the end of all the stages, until all the stages are included. So, we are getting the maximum value here, plus as a result of which, as a result of this allocation, whatever state that we end up in, that becomes an input state, and for which we have already solved, and that is the optimized objective function value that we use. Again, S2, which is the amount of water available at stage 2, can take on only values up to Q, which is the maximum available water, which in this particular case is 6 units. So, we solve this problem for S2 taking on values 0, 1, 2, 3, 4, etc. up to 6, and x2, which is the amount of water allocated at for user 2, can go on up to S2. Let us say S2 is 4 units, then x2, which is the amount of water allocated, cannot be anything more than 4 units. Therefore, x2 goes on up to S2. Now, stage 2 computations, computation is a big word for this, simple calculations is what you understand correctly, then any number of stages you can formulate for a given problem. So, S2 minus x2, as I said, will be the amount of water available for allocation at stage 1, and in stage 1 we have only one user. So, that is to user 1, and F2 star S2, this one, this term here, is the maximum return due to allocation of S2, which means together to user 1 and user 2, what is the optimum benefit or optimum return that you get from such an allocation. And x2 star is allocation to user 2 that maximizes, that corresponds to F2 star S2. There are a large number of possible values of x2, out of which one particular or some of them will lead to F2 star S2, and that allocation we denote by x2 star. So, this is the notation. The DP problems, especially the discrete dynamic programming problems, where the state variables as well as the decision variables take on only discrete values, are typically done through tabular computations. So, let us look at how we write this for stage number 2. For stage number 1, we have completed the computations. So, we will start with, this is for stage 2. Typically, this is the way we write every table. You write the stage number here. So, stage 2, and then you write the recursive relationship. This is called as a recursive relationship, which gives you, for a given state, in that stage, it gives an expression for the immediate objective function value because of the decision that you make here, plus the optimized objective function value for all the remaining stages together. So, f1 star S2 minus x2 is the optimized objective function value that you have obtained in the previous stage of calculations. So, look at this now, S2 is 0. That means, we are saying if S2 is 0, what should be my x2? X2 cannot be anything other than 0, because x2 takes on values between 0 and S2. So, x2 has to be 0. If x2 is 0, R2 of x2 is 0. This is the return that we get from an allocation of 0 units to user number 2, that is R2 of x2 is what we are writing here. And then S2 minus x2. So, 0 minus 0, that is again 0, and F1 star corresponding to S2 minus x2. This is picked up from the previous stage calculations. So, the previous stage calculations we have corresponding to S1 is equal to 0, F1 star of S1 is 0. So, we pick up 0 there. This is 0, and if in the case of 0, everything becomes 0. So, it says that if 0 is available, allocate 0 and you get a maximum return of 0. We look at 1 and 2 and then continue. If 1 is available, that means what we are saying is S2 is equal to 1. You can either allocate 0 or allocate 1 at x2. If you allocate 0, you get a return of 0 from x2, from the allocation x2. If you allocate 1, you get a return of 5. If 1 is available and you allocated 0 to user number 2, how much are we left for the user number 1? 1 minus 0, which is 1, that is S2 minus x2. And if 1 is available, you know what has happened in the previous case, previous stage corresponding to 1. It says that if 1 is available here, you allocate 1 and you will get a return of 7. So, this is what we write here. So, this 7 here 1 0 1, this 7 here is got from the previous stage calculations. So, if S2 is 1 and you allocated 0 to user number 2, you are left with 1 for the user number 1, which gives you a optimized benefit of 7, optimized return of 7. So, the total return corresponding to this combination 0 and 1 will be 7, that is this 0 plus this 7, that is equal to 7. So, R2 x2 plus F1 star S2 minus x2, that will be 7. Starting with S2 is equal to 1, if you allocate x2 as 1, that means x2 is equal to 1, you get a return of 5. Then how much you are left with? 1 minus 1, that is 0, you are left with 0. And corresponding to 0, the previous stage calculations show that F1 star of 0 is 0. So, you get a total benefit of 5 plus 0, which is 5, and therefore, 7 is the maximum value among these. So, this is you pick up a maximum among these. So, this will be equal to maximum of this term, that is what we have written here. So, this is 7 and it says that corresponds to 0. So, x2 star is 0 here. What does it say? It says that at the beginning at stage number 2, if you are given an amount of water of 1, then you allocate 0 to user number 2 is what it says. So, x2 star is 0. You look at 2. If 2 is available, you can either allocate 0 or 1 or 2 to user number 2. If you allocate 0, you get a return of 0 from user 2. If you allocate 1, you get a return of 5 from user 2. If you allocate 2, you get a return of 2 from user 2. If you allocate 0, you are left with 2 for the user number 1, and the optimal allocation of 2 gives you 12 from user number 1. Look at this. User number 1 you have already solved, and you are looking at allocation of 2 at user number 2, and that gives you a benefit of 12. So, you pick up that F1 star corresponding to this, a value of 2, and that is what you get 12. And similarly, if you allocate 1 to user number 2, how much you are left for the user number 1? 2 minus 1, that is 1. And if you have 1 left there, the optimized value is 7. Optimized value corresponding to that stage, which is stage number 1, is 7. Similarly, if you allocate 2 here, then you are left with 0 here, 2 minus 2, 0, you get a optimized value of 0 here. So, what is the total that you get? 12 plus 0, that is 12, 7 plus 5, that is 12, 0 plus 6, that is 6, and pick up the maximum of that. Maximum is 12, and therefore, it says that if 2 is available, you either allocate 0 or 1, both of which give you a value of 12. Like this, for all the possible discrete values of S2, you solve this problem, and then let us say you go to 5, for example, 0, 1, 2, 3, 4, 5. If x2 is 0, 1, 2, 3, 4, 5, then you will get corresponding R2 value. Then this will be 5 minus 0, 5 minus 1, 5 minus 2, etc. And then pick up the associated values of optimized returns from the previous stage. They will be 16, 16, etc. like this. So, the maximum value will be 21 out of all these allocations, and 21, it says that if 5 is available, you either allocate 1 or 2 to user number 2, and you get a maximum benefit, maximum return of 21. So, like this you continue until you exhaust all possible values of S2. What are all the possible values of S2? S2 will be, can be either 0 or 1 or 2, etc. up to 6. So, you complete for all the 6. This completes the calculations for stage number 2. Then you proceed to stage number 3. So, remember, in stage number 2, what did we answer? We answer the question that given S2, which is the amount of water available to be allocated to both user number 1 and user number 2 together, how much should I allocate to x2 such that the total return obtained from the immediate allocation x2 to user number 2 plus the optimized return accruing out of the resultant state S2 minus x2 at stage number 1, these two together will be optimized. So, we are moving in an optimal manner until the end of the horizon, which includes user number 1. So, this is what we answered at stage number 2. Now, we go to the next stage, which is stage number 3. Remember, in stage number 3, we add one more user here, user number 3. So, we have already solved at stage 2, we have solved for the amount of water available S2 here. We know how much optimal benefits that we get. So, at stage 3, we are asking the question, if S3 is available for allocation to user 3, user 2 and user 1 together, how much should I allocate to user number 3 such that the total returns that you get out of this full system is maximized. And that is what we write it as a recursive relationship. F3 star of for a given value of S3 is equal to maximize R3 of X3. You are allocating a value amount of X3 to user number 3, as a result of which you get a return of R3 of X3 plus, because you allocated x3 from an available S3, you are left with S3 minus x3 to be allocated to user number 1 and user number 2 together, and this problem you have solved in the previous stage. In the previous stage, essentially you solved for user number 1 and user number 2 for a given value of S2, and this value of S2 comes from S3 minus x3, and that is the term that we write here. So, this term here F2 star S3 minus x2, S3 minus x3 is in fact the optimized value of the objective function corresponding to the value S3 minus x3, which we have solved for in the previous stage. So, we pick up from the previous stage the associated value S3 minus x3. But there is some interesting feature here. In stage number 2, what did we do? In stage number 2, we said we will solve this problem for all values of S2 going from 0 to q. That is why we solved it from 0 for given values 0, 1, 2, 3 etcetera up to 6. When we come to stage 3 in this particular example, all the users are included, and the state variable, that is the state of the system, S3 is the amount of water available to be allocated to the users included in that stage, and in stage 3 all the users are included. Therefore, S3 will be equal to the total amount of water available. S3 is Q. So, S3 will not take any values other than the total amount of water available, which is 6. So, when you come to the last user in the water allocation problem, such as what I am discussing now, when you come to the last user, that is the last stage, the total amount of water available is, it becomes the state of the system there. So, S3 will be Q. So, you do not solve for various values of S3, but the given value, which is the total amount of water available, 6 in this particular case. S3 is equal to Q, and then X3 goes on from X3 can take on any value between 0 and S3, which is equal to Q in this case. So, this is what we solve in the last stage. So, let us see what we do in the last stage. So, this is what I mentioned. S3 will be 6 units, X3 is the amount of water allocated to user 3, S3 minus X3 is the amount of water available for allocation at stage 2, and stage 2 includes 2 users, user 1 and user 2, and X3 star is allocation to user 3, that results in F3 star S3, much the same way as we did for stage number 2. However, remember here that S3 minus X3 is available for user number 1 and user number 2 together. You do not again go to stage 1 now, you simply relate it with what you have solved for the stage 2, because in stage 2 computations you have already included the optimized value of stage 1. So, when you are doing for stage 3, simply look at the previous table and then pick up the optimal values corresponding to a given value of S3 minus X3. So, this again we do in the tabular form. S3 now takes on exactly one value 6, because it is the total amount of water available to be allocated to all the users included in stage 3, and in stage 3 now we have included user 1, user 2 and user 3 together. In stage 2 we have already solved for user 1 and user 2 together. So, we ask the question, if S3 is available, then how much should I allocate to user number 3? Should I allocate 0, 1, 2, 3, 4 etcetera, such that the total return that you get is maximized. So, I get a return, immediate return of R3 X3 plus, because I have allocated X3 from the available S3, I am left with S3 minus X3 for the next stage, which includes 2 users. I know how much I get from an availability of S3 minus X3 at the next stage, because this is exactly the problem that we have solved in the previous stage. So, this is the recursive relationship. So, we do exactly the same way as we did for the previous stage. We say if 6 is available, I can either allocate 0 to X3 or 1 or 2 etcetera. If I allocate 0, I get a return of 0 from user 3, return of 1 from user 3, return of 8 from user 3 and so on. Out of 6, if I allocate 0, I am left with 6 for the other 2 users, and the other 2 users corresponding to 6 I have already solved. Corresponding to 6, the optimal value is 22 here, I pick up this value 22, and that is we take the sum of these two, that is this term sum, that is 22. Look at this 6, I allocate 1 and therefore, I am left with 5. If I allocate 1, I am getting a return of 5. Where is this available? This data is available right at the beginning of the problem. So, if I allocate 1 from user 3, I am getting a return of 5. So, this is the table that I am using there. So, if I allocate 1, I am left with 5, and that 5 from the previous table you go to 5 and look at the F2 star of 5, that is equal to 21, and that is what we write here, 21, and therefore, 21 plus this 5 is equal to 26. Similarly, if I allocate 2, I am left with 4, and this 4 corresponds to 20, and therefore, the total is 20 plus 8, that is equal to 28, and so on. So, like this you do it for all the possible values of x 3, and you pick up the maximum value out of all these allocations. So, the maximum value in this case corresponds to 28, maximum value is 28, and the particular x star value, particular x 3 value that results in this maximum value is 2. What I mean by that is, it says that if 6 is available, 6 is available at stage 3, then you allocate 2 to user 3 and you get a maximum benefit of 28. This is in fact the maximized value of the objective function after you complete all the allocations. Remember, you should not add this to the value that you got in the previous table associated with any particular allocation and so on, because this value that you get has already included the optimized value for the stage 2, which has already included the optimized value for stage 1. Therefore, when you solve for the last stage, in this particular case stage number 3, this is stage 3. When you solve for the last stage, the objective function value that you get is in fact the optimized objective function value for the entire problem. Now, from this we need to trace back the allocations to different users. The last table here gives you an allocation of 2 units to user number 3. It says that you allocate 2 units to user number 3. So, you understand how we trace back the solution now. So, when the third stage is solved, in this particular case, there are only 3 stages, all the 3 users are considered for allocation. Thus, the total maximum return is 28, which means F 3 star of 6, which is the total amount of water available, is equal to 28. Now, starting with this, we need to trace back. So, just understand how we trace back. 6 is available for allocation to all the 3 users, and this table says you allocate 2 to user number 3. So, how much are we left? 6 minus 2, which is equal to 4 units to be allocated to the other 2 users together, that is user number 1 and user number 2 together. So, we get S2, which is the amount of water available to be allocated to user number 2 and user number 1 together, is Q minus X 3 star, which is equal to 4 units. Then you go to stage number 2 calculations. So, you are saying that 4 is available. So, S2 is equal to 4. Go to stage number 2 calculation, look at what is the corresponding allocation for S2 is equal to 4. It says that if 4 is available, you allocate 1 to user number 2. So, from the previous table, you pick up the optimal allocation corresponding to S2 is equal to 4, which says that X2 star is equal to 1. So, from here you got 6 minus 2 is equal to 4 available for the previous stage, and from the previous stage calculation it says X2 star is equal to 1. So, 4 minus 1, that will be available at stage number 1, that is S2 minus X2 star, that will be 3. With this 3, you go back to stage number 1 calculation, and look at what you should do for S1 is equal to 3. It says if S1 is equal to 3, your X1 star must be equal to 3. So, this is how you trace back the allocations to all the users. So, you got from here X3 is equal to 2, X3 star is equal to 2, then you went to stage number 2 calculations, you got X2 star is equal to 1, then you went to stage number 1 calculation and you got x 1 star is equal to 3. So, you got the optimal allocations to user number 1, user number 2 and user number 3 together, and the optimal return that you get from such an allocation is in fact x 28 units. So, x 1 star is 3, x 2 star is 1, x 3 star is 2 and the total return is 28, total maximum return is 28. This you can verify from the original table of data. Now, this is the data. We are saying x 3 star is, I think we got x 3 star to be 2 here, and let us write down x 3 star is 2, x 2 star is 1 and x 1 star is 3. So, 3 1 2, 3 1 2, user 1, user 2 and user 3. So, we will go to that table. 3 1 2 is the allocation, 3 is 15, 1 is 5 and 2 is 8. So, 15 plus 5 plus 8, that is 28, that is the maximum return that you get. Simply looking at this table, if you wanted to get to this particular allocation, what you would have to do? You will have to exhaustively enumerate. For example, 6 is available, you may say 0 6 0, then 0 4 2, 0 2 4 and so on. Like this, exhaustively you have to enumerate. But the Bellman's principle of optimality makes this such an optimization very simple, because at every stage we are only looking at the computations of the previous stage. So, every time you look up, you relate the present stage calculations with what we have done in the previous stage, and that is how the computations become simple. So, this is the way we trace back the solutions after you solve the problem for including all the stages. So, you included all the users and then solved at the last stage, you solved the problem for the total amount of water available, from which you get the allocation to be made to that last user that was included, in this particular case user 3. Then you will go to the next stage of computation, knowing that from an available amount of water Q, you have allocated x 3 star. Therefore, for the remaining users which are all included in the previous stage, you have an amount of Q minus x 3 available, and go to the previous stage computations, pick up what you should do corresponding to this amount of water available and so on. So, like this you keep tracing back the solution. So, let us look at what we have done in this simple discrete dynamic programming problem. You have a given problem, let us say a n variable problem, you divided that into different stages. So, a n variable problem you have now divided into n stages, each of which having only one variable to solve. In this particular case of water user allocation problem that I just solved, you had 3 users, therefore, 3 allocations x 1, x 2 and x 3. If you had formulated a let us say it was possible for you to formulate a LP problem, then it would have been a 3 variable problem. This you divided into 3 different stages, stage number 1, stage number 2 and stage number 3. At each stage you solved for exactly one variable. In the first stage you solved for x 1, in the second stage you solved for x 2, and from the x 2 arising out of x 2 you know what is the total return. At stage 3 you only solve for x 3. So, at each stage you are solving for exactly one variable. So, what was the 3 variable problem? You converted into a single variable problem to be solved 3 times. Every stage, at each stage you have a policy decision. What is the policy decision in our allocation problem? The amount of water available to be allocated at that particular stage is the policy decision. Similarly, at every stage you have a state of the system at that stage. When we had user number 1, we defined S1 as the state. Now, the state of the system at that particular stage, this example, is the amount of water available to be allocated to all the users included in that stage. Let us say S1. S1 is the amount of water available to be allocated to user 1. S2 is the amount of water available at stage number 2 to be allocated to all the users included in that stage, which in this particular case will be user number 1 and user number 2 together. Similarly, S3 is the amount of water available to be allocated to all the users included in that stage, which is user number 1, user number 2 and user number 3 together. So, at every stage you have a state variable, and in the in the water allocation problem, the state variable simply corresponds to the amount of water available. So, the main characteristics of the dynamic programming are that a n variable problem has been decomposed into a n stage problem. Each stage you are solving for only one variable in this particular case, and one variable can be one vector, one decision vector. And at every stage you have a state of the system, and at every stage you make a policy decision. The policy decision in the water allocation problem is how much to be allocated to that particular user. In for stage number 2 you are making a decision on x2, in stage number 3 you are making a decision on x3, and stage number 1 you are making a decision on x1 and so on. So, at every stage you have a policy decision, at every stage you have a state variable which completely describes the state of the system, at every stage you have an immediate return that comes out of that. So, these are the characteristics of the dynamic programming. The articulation of the problems to fit the dynamic programming algorithm or dynamic programming structure is in fact an important aspect of dynamic programming. As I mentioned in the last class, a given problem you need to look at what are the stages, can we break it into different stages, and can we identify the state of the system, can we completely describe the state of the system at every stage, can we identify what is the policy decision and so on. Now, one requirement for this multi-stage problem is that the state must be, we must be able to transform the state from one stage to another stage. What I mean by that is, let us say you are in stage number n here and this is stage number n minus 1. The state starting with a particular state S n, we must be able to get the state S n minus 1 for a decision that you take in this particular stage. This is a stage n and you are making a decision x n, because of which the state gets transformed to S n minus 1. This is called as a state transformation. So, you must be able to write the recursive relationship, you must be able to identify the state transformation. What was the state transformation in water allocation problem? You had use stage number 1, stage 2. X defines your S1. So, simply Sn plus Xn, and in specific problems the state transformation will be specific to that particular problem. For example, when we go to reservoir operation problem, this may be different. We look at the capacity expansion problem, this may be of a different nature and so on, but essentially it involves the transformation of state at a particular stage, output state which defines the state for the next stage. So, this is called as state transformation. So, you write the recursive relationship, you write the state transformation. And then we have the concept of the recursive relationship. Now, the recursive relationship identifies the optimal decision at stage n, f n of S n for state Sn. So, this is the state Sn in the stage n, given the optimal decisions for each state at stage n minus 1. That is a previous stage for which the calculations would have been already done. For example, in the water allocation problem, we were proceeding in this direction. In stage 1, we had one user. We would have solved that problem and come to stage 2. When you come to stage 2, you have to relate the optimal decision which is for a given S2 for the state Sn, that is S2 here, given the optimal decisions for each state at stage n minus 1. So, stage 1 we would have solved for each possible state at that stage, and that is what we relate it with the optimal decision at stage n. Look at this expression now. Fn of Sn is the optimized objective function value at stage n, and xn is the decision that we are making. So, when we write maximize over xn, this has to be read as maximize over xn, and xn can be a vector. You may have several decisions to make, but in the water user allocation problem, we had exactly one decision, namely the water allocated to the user at that stage n. So, Fn of Sn is equal to maximize over xn, that means you are making a decision on xn. Now, this term you understand correctly. Rn of xn is the immediate return that you get at that stage because of the decision that you make on xn. So, you make a decision of xn, you will get a return of Rn of xn at that stage. Associated with this decision now xn, you have to relate this Fn to Fn minus 1. Now, this decision xn taken on the state Sn transforms the state of the system to the previous stage, from this current stage to the previous stage, and that transformation is given by T of Sn comma xn. Now, this T of xn comma Sn is the state transformation equation. We will call it as state transformation. So, it is in fact a function. It will be a function of Sn, which is the state at that stage n, and xn, which is the decision that you are making given the state Sn. Now, the identification of the state transformation is an important concept here, and that depends on the type of problem, actually the feature of the problem itself. Say for example, in the water allocation problem, we wrote this as the recursive relationship, we wrote as Fn of Sn at any given stage stage n here. What was the state variable? The state variable was the amount of water available at that particular stage n. We wrote this as maximize over xn, let us say n was 2, second stage, and x2, which was the water allocated to user number 2, and you get a return associated with that decision xn plus Fn minus 1, which is, if you are looking at stage 2, F1, n minus 1 will be F1 of Sn, which was the amount of water available to be allocated at stage number 2, which consisted of two users, namely user number 2 and user number 1. Because you allocated x2 there, what is the amount that is left for user number 1, which is stage number 1? It will be S2 minus x2. So, that is the idea there, and therefore, the state transformation for the water allocation problem is simply Sn minus xn. So, this is how we define the state transformation for a given problem. In the water allocation problem, I repeat, the state transformation is simply Sn minus xn. So, if you have several users, every time you relate this with the previous stage. identification of the state transformation is an important exercise in writing the recursive relationship. Different types of problems will have different state transformations, as we will see in the next problems that I will discuss. For example, the reservoir operation problem may have mass balance or continuity starting with a particular storage in a particular time period. You may want to relate it with the storage in the next time period, which in the backward direction will correspond to the previous stage, and so on. So, depending on the type of the problem, you must identify the state transformation. State transformation essentially indicates the transformation of the state starting with Sn in stage n to state Sn minus 1 in stage n minus 1, because we are relating it to stage n minus 1 in the backward direction. Once you identify the state transformation, it is easy for you to write the recursive relationship, and writing the recursive relationship is the single most important feature of a dynamic programming. That is, identification of the recursive relationship is the single most important exercise that you do in dynamic programming. Once you identify recursive relationship, the problem becomes very simple, because in the discrete dynamic programming problem, states Sn are discrete, decisions Xn are discrete, and therefore, once you write the recursive relationship correctly, all you have to do is solve this recursive relationship for various values of Sn, and each value of Sn corresponding to a number of discrete values of Xn. So, that is the concept of a state transformation and the recursive relationship. Now, there is a requirement here which is often overlooked, and we tend to mechanically solve the problems. See, what does this mean? This means that the objective function is in fact separable. That means, what we are doing at stage n and what we have done at stage n minus 1 can be separated with one set of decisions taken at each of the stages, which means what? Which indicates that the objective function must be separable. For example, look at this kind of function. I will say x1 square plus x2 square plus etcetera xn square. This I can break it into different stages. At each stage I may consider only one of the variables. So, I will solve for xn, then I will solve for xn minus 1, etcetera. So, this is a separable objective function. However, I have some function like this. So, this is separable. Let us say I have a function like this, x1 x2 plus x2 x3 plus x3 x4 and so on. If I have some such function, although I have different terms associated with different stages, I may still break it into different stages, but the objective function is not separable, because any stage, let us say this, I have a which is dependent on the previous variable x3, which appears in both the stages. Therefore, this is not separable, and therefore, these problems are not amenable to be formulated as dynamic programming problem. So, one requirement is that the objective function must be separable. And optimal decisions. So, finally, what we do is progress from one stage to another stage, and then complete all the calculations, complete all stages. Once you reach the final stage, you get the optimal objective function value, and from that you trace back the solution. So, the optimal decisions are traced back. Now, the solution moves backward or forward. I say here, there are certain problems where you need to move only in the backward direction, because the last stage, let us say you are talking about time horizon. you may fix the boundary condition, so to say, at the end of the last time period. So, that time period boundary conditions may be known, and then starting with that you may proceed backward, or your initial storage condition in the case of a reservoir operation problem may be known, in which case you come from backward in the backward direction, and then when you do the last stage calculation, you will use this as a condition that needs to be satisfied. If on the other hand you are looking at the shortest route problem, let us say, then you may it may be advantageous to proceed in the forward direction. So, you may either proceed in the backward direction or the forward direction. However, your definitions of the state variables and the decision variables must be clear. What I mean by that is that given a particular problem, you may either proceed in this direction, that is, you may specify S1 various values and solve for this, and then go to this second stage for various values of S2, you solve for these two together and so on. Or you may want to proceed in this direction, in which case you may start with Sn minus 1 and relate it to Sn. Similarly, Sn minus 2 related to Sn minus 1 and so on. So, depending on the physical problem that you are solving, there may be advantage to either move in this direction or in the backward direction. I will give another example of reservoir operation, where the direction of movement will become clearer. If we place one type of boundary condition, so to say, that is at the end of the time period, if I fix a storage, it may be advantageous to move in certain direction. If at the beginning of the time period, if you fix the condition, it may be advantageous to move in another direction and so on. So, the much unlike the linear programming problems, there is some articulation that is involved in the dynamic programming formulations. It is not just an algorithmic way of solving as we did in the linear programming problem. You must understand the physical problem correctly, see whether you can divide the problem into several number of stages. At each stage you are making exactly one policy decision, and that is related with the previous stage computations and so on. So, you must make sure that the objective function is in fact separable, and you are able to write the recursive relationship, you are able to write the state transformation equation from relating the transformation of the state from one stage to the next stage. In fact, the state transformation, the way you are writing the state transformation will also decide in which direction you would like to proceed in the computation. So, the backward direction as well as the forward direction you can move depending on the type of problem, and the Bellman's principle of optimality is valid in both the cases, but the way we state may be slightly different. It is essentially that given the state of the system, you must proceed in an optimal manner. Whether you are proceeding in the backward direction or in the forward direction does not matter. All it states is, do not worry about how you arrived at that particular state, you must proceed from starting with that state. In that stage, you proceed in an optimal manner. So, this is the governing principle of dynamic programming. In the next lecture, I will cover, using the dynamic programming, an important example for in water resources, that is the reservoir operation problem. So, next lecture we will start with the reservoir operation problem, we will solve with dynamic programming, and then see how we use this discrete dynamic programming problem for single reservoir operation. We will take it as an example, and then in the subsequent lectures we can talk about what we call as steady state operation and so on. So, this is the first example that I will be dealing with reservoir operation. So, I will give some introduction to what we mean by reservoir operation, what are the decisions that we need to take, how we define the state variables and so on. So, essentially in today's lecture, we completed the water allocation problem that we took up in the last lecture, and we saw how we formulate the state transformation equation, how we formulate how we write the recursive relationship that relates computations from one stage to the next stage and so on. Remember, in the type of problems that we are solving, at any given stage, you just relate the computations with what we have solved in the previous stage. So, just look up the previous table for the solution, pick up that particular objective function value and plug it in here. So, like this, from one stage to the next stage to the next stage, your computations proceed. However, you have to store all the stage computations until you complete all the stages. It is not that the moment I solve this stage computations, I will discard all the others except I will retain the previous one, because only the previous one is not necessary. Finally, you will have to trace back the solution, and therefore, the computations that you have done right from stage number 1 to all the stages until this point, stage number n, have to be retained, because finally, when you solve the last stage computation, you have to trace back, and the trace back involves tracing back solutions in all the stages. We will see what it implies in terms of computer memory, in terms of the computer time and so on. When I deal with other problems, we will discuss that feature. So, we will continue the discussion on dynamic programming in the next lecture. Thank you for your attention.